Okay, we've been talking about logs and exponential functions, and I want to, today might be the last day of talking about that stuff, or maybe, I don't know, depending on how much. We're almost to the end in any case. What I want to talk about today is logs and exponential functions of different bases, not just the natural log, but the other logs, which I'm sure you've heard of before. Although I had a few more things left over to say about e to the x. So at the very end last time, we came up with this formula for the derivative of e to the x. Derivative of e to the x is e to the x. This is everybody's favorite fact about e to the x. Yes, I just, my mind just raced into something. This is everybody's favorite fact about e to the x, but I don't know if you know anything about the history of logarithms and e to the x. Logarithms were invented in the 1600s, early 1600s, or the late 15s. But anyway, that was before calculus existed. So actually people were talking about logs and e to the x before anybody did the derivative of anything. So it's to me, this is the reason why anybody cares about e to the x, is because the derivative of e to the x equals e to the x. But actually that's not sort of a historically accurate way of putting it. More accurately, people had been talking about e to the x for 100 years or so before they realized that this was actually true of e to the x. All right, I don't know if anybody cares about that. This is just straight up the derivative of e to the x. Now this rule we usually use in combination with the chain rule if you have other stuff inside of the exponent. If there's some like extra business up inside the exponent, the answer is not just e to the g of x. Again, you have to do the chain rule, which means multiply times the derivative of the stuff on the inside. So the answer is e to the g of x times g prime of x. So you keep it the same in there and then separately multiply times the derivative of what was on the inside. And that separate multiplication is not part of the exponent anymore. It's just a separate thing. All right, I think our textbook sort of writes this as a big formula to memorize, although in my opinion, I don't really have this memorized per se. I have this memorized, and then I just know that you have to use the chain rule sometimes when you have more stuff on the inside, and that's what you get. But however you like to think it through. So for example, the derivative of e to the 3x squared plus 7x plus 2 is, just using what you see in the box, the same thing again, e to all that business, and then times separately the derivative of the business, which is, make sure you have these parentheses here, 6x plus 7, like that. So this is the derivative of e with some other stuff inside of it. All right. You want to try some of those? These are, there's not too revolutionary here, and I assume that you've done things like this. So how about find the derivative of each? I got 4 of them to try. In no particular order. See what you think. I'll give you a few moments, and maybe I'll walk around and see how everybody feels about it. this is, this up here means x to the power 1/2. So we want to get rid of that. 1/2 comes down, and you have x to the 1/2. Okay. Alright. Then you go here. Yes, yeah. Okay. Feel free to chat with your neighbors about it.
Yeah, let's go here for a second.
F prime, so at the top, F prime of x gives you f prime is g prime of x, and f of x divided by dx. I don't know. I'm gonna know here.
Wait, what should we play low behind my side? Let's do the third one.
You need to do a product x and then 5.
I said, use the 5x, this one, use the quotient of 5x.
Wait, did you get oh, I got 5x. Times 5x.
I mean,
Then,
Is it 3x? No. I just got
what about this? E product is that? Is it e to the 5x times 5x plus e to the
I remember that. We used to say low behind, tidy low.
So,
Squared, right?
root
Wait,
of it.
so is it
So 1
F
times
prime?
no, it's not f prime of
Is
g,
that
it's
this?
just f
F prime
prime of
of
x,
g.
f prime of x times g.
Yeah, that's what yeah, okay. Yeah, when you said off G, I was.
I'm gonna do
That's okay.
It's the way I can just do the reference and they just cross those. So you get it's like this plus yeah.
Yeah, it's like the product. And then it's over just normal G. Just go, I'm gonna just. That one. And so over G squared. Oh, yeah. Like the second round. Yeah.
All right, can we talk about these? I hear some lively discussions. That's great. So the first one, e to the root x. As I was walking around, this is what I saw a lot of people said, e to the root x. And then root x, of course, is x to the 1/2. So this becomes the derivative of the inside, which is that. All right? Actually, I don't like that answer. Anybody have a suggestion? I saw a lot of people wrote this. Yeah?
1/2 root x.
Nah, I don't care about that. I mean, that's fine if you do that, but I have no problem with negative exponents or radical in the denominator. Although you just made a radical in the denominator when you said that. Yeah, I don't care about that. Any others?
Do you want us to move so it's 1/2 E?
Nah, I don't care about that. I'm not talking about simplifying. There's actually, like, what is written there is technically speaking wrong. It's straight up not true. Yeah. Yeah. The derivative of that equals that other stuff. It's not true that just, I mean, if you write this, it's just straight up false, right? It is not. This is something that often happens. I'm sure none of you would do this, but in my applied calculus class, right before the test or something, they're like, wait. E to the x is just e to the x, right? And I think, well, yes, but that's not what you mean to ask, but the answer is still yes. The derivative of e to the x is e to the x. This is correct. And then they're like, yeah, and ln x is 1/x, right? I'm like, well, the derivative of ln x is 1/x, but not ln x is not the same as 1/x. If it was, then we wouldn't talk about ln x because 1/x is a lot easier, right? So the derivative of this equals this. Great. This one. Now, sometimes, here's a variation. You know, I said that. If you want to just do this, that's totally fine. I mean, this is still true, I suppose. Just don't put an equal sign here because they're not equal unless you put an operation on one side, then they are equal. All right, whatever. I see similar things when people write something like, if I have 3 plus 2 plus 5, what is that? Yes, 10 is the answer. But sometimes people are like, this equals, I'm trying to think of how, they say, okay, I have to do 3 plus 2 plus 5. So I do 3 plus 2 equals 5 plus 5 equals 10. I know what you mean, but you shouldn't write that because that's not true what you wrote, right? This is, you know what I mean? This is the kind of thing that I think about sometimes. Maybe nobody cares about this. This says 3 plus 2 equals 5 plus 5, which equals 10. That's not all true, right? Like, this right here all by itself would be true, or this right here all by itself would be true, but when you string it all together, it's not true anymore. So, these are the things that I think about sometimes. Whoa, sorry. It's because I have deep and abiding respect for the equal sign, all right? You want to use the equal sign, you should do it right. Okay, this one here, the derivative here, you must use the quotient rule, which I hope everybody remembers. You get, first of all, this, what you started with, because that's how we handle e to some power. And then the quotient rule, the way you might write it slightly differently, but I write it as the bottom times the derivative of the top, which is 3, minus the top, 3x, times the derivative of the bottom. Sorry, I'm running out of space. A. The top times the derivative of the bottom, which is 2x, all divided by the bottom squared. X squared plus 1 squared. That's the quotient rule. I hope everybody remembers the quotient rule. I will expect you to remember the quotient rule on a quiz or something, although it might never come up. I mean, we don't usually do that kind of thing in this class, but I would expect you to know it. All right. The next one is a product rule, because it's a product. So here, how about this? This becomes, so the way I write the product rule, and you can rearrange it slightly, the first thing times the derivative of the second thing, which would be that, and then plus the second thing, e to the 5x, times the derivative of the first thing, which is just 1. That's the derivative of x. So that's the product rule. I didn't write the derivative operation, but I also didn't use the equal sign, so all bets are off. You don't know what the arrow is supposed to mean. It means derivative right now. All right, and then e to the power of sine x. This is a fairly simpler compared to the other ones. It's just the same thing again, times the derivative of the inside, which is cosine x. So I hope that's what you said. All right, great. These are a bunch of derivatives involving e's. We might as well talk about antiderivatives. Let's just do one example. So because of the derivative formula, derivative of e to the x equals e to the x. So if you read this the other way around in terms of antiderivatives, it means the antiderivative of e to the x equals dx, of course, equals e to the x plus c, if you want to get all the details right. Okay, so this is, another antiderivative formula to know about. Now, what if, in addition, instead of just e to the x, what if you had some other business inside of the exponent? Actually, in the case of an integral, it becomes much harder. There is no standard kind of chain rule thing that you have when you're doing antiderivatives. The closest to that you can do is the u substitution. So let's just try one. So let me just say, if it's something like e to some complicated stuff here, and it's in an integral, then usually you have to do the u substitution. All right. Which is kind of the version of the chain rule for the antiderivative, although it's a lot harder to do than the chain rule. Let's try one just real quick, and then we'll get on to something else. How about this? Integral x squared times e to the x cubed minus 1. What should I pick for the u? Anybody see how this is going to go? X cubed minus 1, she says. Yeah, generally speaking, you should choose the u to be the inside of something. If you see parentheses or square root sign, or in this case, an exponent, you should choose the u to be the inside of the exponent. That usually is going to work. Okay, then the du is the derivative of that, 3x squared dx. And as I usually do, I'm going to divide that 3 over to the other side. So this says 1/3 du equals x squared dx. And then I can see over here already, I'm starting to feel good about this, because I have, this is going to be e to the u, but then I also have x squared and dx, which is going to be what I want to see for the du part. So this. Just directly plugging the u in looks like x squared e to the u. And then if I kind of shuffle things around a little bit, it'll say e to the u x squared dx, and then x squared dx, I just said, is 1/3 du. So this is e to the u times 1/3 du. And then the 1/3 can pull out front, like so. All right. What should we do next? So the substitution is finished now. Everything is about u's rather than x. What's the next step? Yeah, do the integral. And what is the integral? The 1/2 stays like that.
I mean, 1/3.
1/3?
Yeah.
Yeah, I wrote 1/2. Sorry. 1/3. Thank you. What happens when you do the integral? It's just e to the u. Yeah. This is a weird looking step. You might think I just like the integral sign disappeared. It's because the integral of e to the u equals e to the u plus c. Great. And now we just got to plug in the x's. So instead of u, we have x cubed minus 1, and that'll do it. So it's 1/3 e to the x cubed minus 1 plus c. There you go. You'll have some more practice with these ones on the homeworks, but I hope that's seems all right. All right, great. I think we can move on to the next section then, and that is, as I said at the very beginning, let's talk about logs and exponents using different bases. All right. I think this is something that everybody knows. We have talked about the natural log, and we have talked about the exponential function with the base e, but there are others. So let's talk about other bases. Other bases. So this e to the x, this is the exponential function with base e. This is the language that we use. The base in an exponential function, you know, the base is just like the number that you see down below, and the other one is called the exponent. But this is the exponential function with base e. And of course, there are other exponential functions, so we can do others. You know, like 2 to the x or 10 to the x. These are probably the most important single exponential functions that people use. 2 to the x, 10 to the x, etc. Whatever base you want to put there. Actually, the base b to the x for any b being positive, for any b greater than 0. It is important that the base not be negative, because weird things can happen if the base is negative, and maybe I'll say a little bit about that. But one thing that is something, in my opinion, not a lot of people mention when you learn about this stuff in high school, or even maybe even before high school, you first talked about these functions. These functions actually take a little bit of work to give real definitions for them. For instance, what is the definition? What is the definition of 2 to the power 3? This is an easy one. This is one that kids learn. How would you explain to a kid what does 2 to the power 3 mean?
2 times 2 times 2.
Right, it means 2 times 2 times 2, and this is repeated 3 times, right? What about 2 to the power 1.5? What's the definition of that? This is immediately weirder. Don't say 2 times itself 1.5 times. That doesn't make any sense. 2 times only that much of the next one. Certainly that does mean something, right? You got an idea?
Don't you do like the root or something?
Yeah, this has something to do with the root of something. Also don't say you just do that on your calculator. I mean, that's true if you actually want to know what the value is. This is some kind of root of something. Yeah? Do you have a specific?
Well, wouldn't it be like 3 to the 3 halves?
Yeah, I think the appropriate way to think of this is to say this is the same as 3 halves, and then you know how to interpret a fraction inside of the exponent. I mean, this is not obvious, but the interpretation of this is it is, one way to think of this is that, and then this is root 2 to the power 3, all right? And in general, you can do this for any rational number in the exponent. So if the exponent is rational, that is, if you can write it as a fraction, then what this, so, sorry, to finish the definition, if I were explaining this to a kid, I would say now this actually does make sense. It's root 2 times root 2 times root 2, 3 times. That's what that means, right? For any rational exponent, if I'm doing something like 2 to the power, p over q, if it's a fraction up there, the way you think this through is it's 2 to the 1 over q to the power p, and that inner thing is the q root of 2 and then to the power p, right? This is the true definition of an exponent of something else, right? That's the qth root, not the cube root. The qth root, all right? You ready to get crazy here? Anyone know what my next question is going to be? We started with, if the exponent is a whole number, it means that. What if the exponent is rational? It means that. What if the exponent is irrational? And this, in my experience, is something that not a lot of people talk about. What does that even mean? 2 to the power pi. Does it mean anything? Yes, it does, but it's not obvious what that's supposed to mean. Have any of you ever thought about this or talked about it in high school, maybe? It better mean something, because we do want to talk about this as a function where you plug in any real number and you get an answer, right? So 2 to the pi has to mean something if this makes any sense at all, right? Now, actually, I will say e to the pi to us already does mean something, because e is defined as the inverse of the natural log. And so e to the pi means it's the value of x, which makes log of x equal to pi. And that you could find as the area under the curve of something or other. So actually, it does make sense in that context. But what is, does anybody know? Anybody ever thought or talked about this? You can ask your friends. I don't know if high school math teachers just don't want to get into this, or this can be defined in various ways. So this could be, what I'm about to say is not how we're going to talk about this definition, but this could be defined as a limit. This is a little weird. You can take a limit as x approaches pi, where inside, this is a strange kind of limit, but in here, use rational approximations. What I mean by that is you go, start with just like 2 to the 3, 2 to the 3.1, 2 to the 3.14, 2 to the 3.141, etc. You keep on doing this with closer and closer versions of pi, but those things up there are all rational. And so each of these numbers actually does make sense. And then you can take the limit of these numbers and get an answer. That's one way to do it. Actually, a better way, and this is the way that we are going to discuss this, involves a little trick, just because of the fact that the way that we define e to the x as the inverse of the log, and the log is defined as the area under the curve of something, we can define 2 to the x in terms of e to the x. So 2 to the x is defined as e to the x times ln of 2. And if you know something about simplifying exponents, these are supposed to be equal anyways, all right? But the benefit here is that here, this side, this is already defined for any x, even irrational. Right? So this is what we are going to take as the definition of that function 2 to the power x. And so what that means is 2 to the pi. What does that mean? You can tell your friends at dinner. when they ask you, don't they ask you all the time, what does 2 to the pi even mean? Maybe they don't ask you that. But what it even means is this, e to the pi times natural log of 2. Where natural log of 2 is just some specific number which it represents the area under the curve of something or other, which you can calculate if you want to using Simpson's rule or something. Multiply that by pi, and then you do e to this power, and what that means is it is the inverse of the logarithm function. Right? This is complicated, but it actually makes sense as a definition. Unlike, alternative notions, most people don't really even know what that's supposed to mean. All right, so this is an exponential function. I'm going to say this more specifically here. For some number b greater than 0, b is going to be the base. The exponential function with base b what if I use my highlighter, huh? Isn't that cute? The exponential function with base b is defined in this way. B to the x, the definition is b to the x e to the x ln b. That's the definition of b to the x. All right. This is called the exponential function with base b. By the way, does anybody know, here's another fun fact, why does the b need to be positive? Anyone know what's the problem if you were to use negative numbers for the b? There are, or 0? Yeah? All right. There are problems, yeah?
Can't take that natural log.
Yeah, actually, yeah, if you're using this definition here and the b was negative, you would end up saying, like if the b was -1, this would say e to the x times ln of -1, and that's not allowed. Ln of a negative number is not allowed. Yeah, there are also reasons, like even if you're not using this as the definition, let me just say negative b is not allowed. If you allow negative b, then that would allow you, so this would let you do something like -1 to the 1/2 power. And this is the square root of -1, which is not a real number. So if you're using negative numbers for the b, you're going to have problems with, so this is not a real number. Although, strange but true, this is a real number, right? So if the base of your exponential function is negative, then it's like sometimes you get real numbers and sometimes you don't, and you end up getting something very weird. And in any case, this b to the x is not an ordinary function of real numbers. Yeah?
Are we going to do imaginary numbers?
No,
Or-
not in this class. I mean, you can talk about it if you like, but
It's okay, we don't have to.
yeah, all right. Yeah, I mean, so if you are a math major, which I heartily would recommend, we have a class called complex analysis, which is the whole class is about imaginary numbers, and it involves doing calculus using imaginary numbers and other things. So we don't. I would say for our purposes, we don't need to get into it. All right. And there are actually definitions, if you know something about imaginary numbers, like there actually is such a thing as the natural log of a negative number. The answer is imaginary. And you can even take the natural log of an imaginary number. It's good stuff, but not for this class. All right, can I just say, so basic facts about the exponential function with a different base. We have similar exponent rules. Just like e to the x, it has all the same kinds of properties, like b to the x plus y equals b to the x times b to the y, etc. These are all basic exponent rules that everybody learns about in high school or maybe before. But I would like to see if we can justify these using the definitions that we're actually using. So the easy way to say this in sort of how I would explain this to a kid is this says b to the x plus y. This means b over and over again, b times b times b times b, x times, and then separately b times b times b, y times. So how many times total is that? Well, it's b times b itself x times, and then also y times, which is why it's x plus y times up here. But that whole argument only makes sense when you're talking about whole number exponents. So how can you demonstrate this for non-integer exponents, non-whole numbers? So this, to prove this, it's very easy actually. You do have to use the definitions. So this is equal to e to the, what was it? X plus y ln b, right? And now I want to simplify that and somehow eventually end up with this over here. Anybody have a suggestion? How could I simplify this? Yeah?
You can take the x plus y out, put it before the e.
I don't think you can do that.
You take it all out and put it before? No.
No, something a little simpler maybe.
Could you cancel e and ln? And that would leave you with x plus b times x plus y times b.
No.
Can you just distribute?
I would distribute. Yeah, this is much simpler than what you guys are. Doing some of these things, you would end up doing like too much. If you cancel, somehow turn this into x plus y times b, that's definitely not like everybody knows. I hope it's not true that this is equal to that, right? So that can't be right. E should distribute. Yeah, let's distribute. Sorry, I'm red here. Distribute. That would be e to the x ln b plus e to the y ln b. All right. What else? We can use our facts that we already know about powers of e, right? We talked about those last time. Anyone have a fact about powers of e that we could use here? Did she say e, bruh? That's what I heard somebody say. Yeah.
We do e to the x ln b times e to the y.
Yes, e to the x ln b times e to the y ln b, right? That's our rule about e to, if there's a sum inside the exponent, you can split it up like that. E, bruh. And then what to do with that? What can I do? What is e to the x ln b? That is the definition of b to the x, right? And the other one is the definition of b to the y. And that's what we wanted, right? We start with b to the x plus y and end up with this. B to the x times b to the y. Shun. Right? We got 10 minutes. I got one. Can you try one? How about this? Try to prove it should go more or less the same way. ab to the power x equals a to the x, b to the x. And don't just tell me this is like an obvious fact that you know about exponents, because we're using a weird definition of what the exponent even means. See if you can demonstrate this. Maybe we can we just do the very first step all together? What's the first step? You should just write what that means. ab to the power x. Can anybody say? Yeah?
E to ab ln. Wait. Shoot.
Yeah, I always confuse this a little bit. The true definition is here, right? So this is what you're trying to use.
Oh.
Where
Yeah,
in our case it's ab down there.
Yeah, e to the x ln ab.
Right.
Yeah.
E to the x times ln ab. Yeah, and then see where you can go from there. Your next step should be one of our rules about ln. give you one more minute. All right, your 1 more minute is up. Can somebody say what should we do next? Maybe someone I haven't heard from yet today. I appreciate all the enthusiasm. Yeah?
Do you put like the x on the outside and then you have like in parentheses ln a plus ln b?
Yes,
in the
right.
exponent?
This is one of our properties of the log. ln of ab is the same as ln a plus ln b. Yeah, great. I hope that's what you did first. And then I think it makes sense to distribute. Okay. E to the x ln a plus x ln b. Where do we go from there? Anybody work this one out? What'd you do next? Yeah?
You do e to the x ln a times e to the x times
Right.
e to the x ln b.
Actually, it's the same rule that I did up here, right? When you have addition inside the exponent, you split it up into multiplications. So e to the x ln a times e to the x ln b. And then what is that? This actually is what we're looking for, right? E to the x ln a, that's the definition of a to the x. And e to the x ln b is the definition of b to the x. Great. All right, there you go. I hope you did something like that. I might occasionally ask you to proof things on the homework or something. Just at this level, though. I mean, this is more or less. You don't have to have some kind of big idea and write a big dissertation about it. All right, we got 5 minutes left. That's enough time just to finish up this little bit. What I'm talking about here. What about derivatives and integrals of these other exponential functions? So what about derivative of b to the x? All right. Now, you probably learned a formula for this at some point in your life. But we can actually work this out. You don't have to know a formula. Using the definition of b to the x. This b to the x, its definition, what it means is e to the, I always have to think a little, e to the x ln b. It's easy to put the b and the x in the wrong places, but that's the definition of b to the power x. And this now, we can do the derivative using the chain rule, just like all those ones that you did before then I was walking around. So it is e to some power with some weird stuff up there, which means my answer is, first of all, you get the same thing again. And then separately, I multiply times the derivative of the inside of that stuff. You have to be a little careful about what exactly is the variable and what is a constant. Up here, x is the variable, and it's x times this as a constant. ln b is a constant. So what are you going to get as the derivative of the inside here? 1. Yeah, 1 times ln b if you like. This is x times a constant, and the derivative of such a thing is just whatever that constant is. You know, if it was 2x, it would be 2. Here it's ln b times x, so it is just ln b. That's what I just did. That's the chain rule. All right. So that's the answer. Although it's a little nicer, you will notice e to the x ln b is the same as b to the x, right? That's again the definition of b to the x. So this is the way that people typically write this formula. Derivative of b to the x is b to the x times ln b. So that is worth remembering. Maybe you already knew that one, but this is the derivative of an exponential function other than e to the x. All right. For example, how about the derivative of, let's try 4 to the power 3x squared minus 2x. Now, if it was just, actually, would you mind a preliminary example? That's a lot easier. What about just derivative of 4 to the x? Just plugging in directly using b equals 4, it is 4 to the x times ln4. And ln4, of course, cannot be simplified. It's just some number. You can plug it into your calculator if you want to know what that number is, but you can't do anything else with that. What about this one? 4 to the power, that other stuff, all right? I'm going to have to use this rule again, in addition, together with the chain rule, right? So when I see 4 to this business, what I get in the answer is just the same thing again times ln4. So I'm going to write 4 to the 3x squared minus 2x times ln4. So that was just using the formula as is, where b is 4, and instead of x, I have that other stuff, 3x squared minus 2x. And then we got to do the chain rule, times the derivative of the inside of the exponent. And that is 6x minus 2, like that. So this part comes from the chain rule. All right. If you prefer, so here I was thinking of it as I'm using the formula in the box and also doing the chain rule. If you rather just remember formulas with these things built in, you could write this, and I think you will see this formula in our book, although I don't usually think of it in this way, but if you like, you can. If you have some extra stuff up top, you do the normal formula, which is to say you get the same thing again times ln b, and then times g prime of x, right? That's what we just did. You leave it, make sure you leave it the same up here. This is the original g, this is the derivative g prime. All right, and I think that will do it for us for today. A little bit more about this next time, and then we'll move on to something else.